Welcome to fall semester review. At the beginning of the year, we started out with chapter 1. So as I mentioned yesterday, this comprehensive test that you will take tomorrow will be chapters 1, 2, 3, 4, 5. Chapter 6, sections 1, 2, and on section 5, only the parts of vascular and hybridization, not intermolecular forces. We'll do that in January. Okay, so in chapter 1, it's a whole bunch of review. A lot of it is review of physical science and the stuff that you had in biology that pertains to chemistry. My recommendation is, first of all, know your definitions. As I mentioned yesterday, chemistry, we don't do a lot of, straight definitions. So you shouldn't get hung up on knowing every single word of a formal definition. That's not what I mean. Just be familiar with what the stuff is. And I think that should be no problem for you guys because you kind of learn it as you go through the work. Branches of chemistry, as I mentioned yesterday, you may have questions like, if you are studying the energy released by some chemical reaction, you would be working in physical chemistry, because if you look on page 4, physical chemistry is how energy interacts with chemical and physical changes. If you are, working with carbon substances, that would be organic chemistry. If you're working with substances that do not contain carbon, you would be working in inorganic chemistry. So y'all good with that? If you were studying cellular respiration, what branch of chemistry would that be? You studied it last year, right? Biochemistry. Yeah, biochemistry is the study of chemical reactions in a living organism. And remember, science is not compartmentalized. That's one thing academic, and we can't help it. It kind of is what, it's kind of really, to get all of the concepts, I personally think that you have to have a biology class, you have to have a chemistry class, you have to have a physics class. But in reality, all the sciences are intertwined. No matter what work you do in science, you've got a little physics in there, you've got a little chemistry in there. Biology is the most complex science. If you think about it, it makes sense. Living organisms are quite complex, right? Most living organisms. Any movement of a muscle, well, that involves physics. You eat your cheeseburger here in a little bit, well, you start getting sleepy because your body's taking energy to put into digestion. Well, that's physical chemistry, the energy change, and biochemistry, right? Okay, enough of that. Basic research, applied research, and technology. Remember, basic research
is what you do by yourself. Right?
Yeah, it's for knowledge only. Yeah. You're not trying to solve a problem. Just like, oh, I wonder what that is. So you run experiments. It's just for curiosity. Here's Rena. Applied research That is where you're trying to solve a problem. You know, like, alternative fuel sources. You know, research with that. Well, that's applied research because there's a certain problem in mind that they're trying to solve. Or finding a cure for cancer, you know, a specific problem. Technology. Technology, anybody? Is where that research is used. Research is science. Technology is the application of research or science. What is this thing doing? Hang on, let me see what's going on here. This thing on the corner. I don't know where she is this period. Can you text her or something? Okay. I want to say she's like in art or something. She may not be able to get out. All right. Sorry about that. On page 6. As you know, as I said, definitions. What is matter? Anything that has mass and takes up space. What is mass? Amount of matter. Atom is the smallest particle of an element, right? A molecule is the smallest particle of a compound. A compound is 2 or more elements chemically combined. Here are 2 definitions that people forget all the time. They're on page 7. Extensive and intensive properties. EX means out, right? So an extensive property depends on something else. And that something else is mass. How much sample you got. An extensive property depends on sample size. Intensive does not. So examples of this, examples of extensive properties would be like heat, mass, weight, intensive properties would be like boiling. When I say BP, I mean boiling point temperature, melting point temperature, and density. Oh, another good one for extensive volume. Anything that is going to change as the size of your sample changes is going to be an extensive property. X means out, depends on something else, right? Intensive properties never change. Water, it doesn't matter if we've got a little tiny 30 milliliter beaker of water or if we've got a whole bathtub of water. It's going to boil at what temperature? 100 degrees Celsius, right? Does not matter how much of it we have. That's an intensive property. Kendall?
It depends on what?
The sample size, the amount of your sample. You're welcome. Okay, moving on. Physical change, chemical change. Okay, which one changes the identity of a substance? Chemical. Chemical change changes or alters the composition. What's composition again? Yeah, what it's made up of. So what would be an example of a chemical change?
Burning.
Burning. Can I think of another one? Huh? Melting? No.
I said rusting.
That'd be physical. Huh?
I said rusting.
Rusting, yes, I'm sorry. Remember, too much rock and roll. But I like it. Okay. Rusting. Digestion. I mean, I won't get gross, but, food doesn't come the same way it went in, does it? I said that on video too. Okay, physical changes do not change the composition. So, Kennedy, melting. You melt a piece of ice. Did it change its composition? What is the composition? Water, right? Okay, so that means, boiling is still water, right? All changes in state of matter are physical. So, freezing, melting, boiling, condensation.
Cutting.
Yeah, cutting, which, is not a change in state of matter, but yes, cutting something. You cut your hair. Is the hair still made up of the same molecules? Yeah, yeah. You bleach your hair. What would that be? Is that physical? It's chemical. Yeah, it's chemical because you are changing the bleach, the peroxide goes through a chemical reaction with the pigments in your hair, whatever molecules those are. So yeah, bleaching, dyeing, those are chemical. Okay, any other questions about that? Okay. Now, you guys ought to know, I'm not going to throw curveballs at you. That's not fair. We're still in this journey of chemistry, right? So don't freak out. Be prepared, but don't freak out. Matter. Let me pause this a second, y'all. All right. This is a diagram, a flow chart on page 11. I like it because picture's worth 1,000 words. Everything's right there at a glance. I'll reconstruct it briefly on here for the video. Matter. We got mixture and a pure substance. The way you can tell which one's which, you got your sample. Skinner brings some sample, some stuff in here to us, right? And wants us to identify it. Well, the first thing we would ask ourselves is, can it be separated with a physical change? If the answer is yes, it's a mixture. If the answer is no, it's a pure substance. Now, like, remember, I brought out that jar of stuff, and I asked you what it was, and you took guesses, and then we stuck a magnet to it, and it pulled out a bunch of iron, right? So we saw that it was a mixture, because we were separating it with some physical property, magnetism. Pure substance is either an element or a compound. We know that an element is one kind of atom. Compound, two or more elements, chemically bonded. Now we know what that means. Okay. All of your elements are on the periodic table, right? Okay. Mixtures. Mixture can be homogeneous or heterogeneous. Homogeneous is uniform. You cannot tell one part from another. They are also called solutions. A solution is a homogeneous mixture. So, sugar water, brass, steel, air, those are all solutions. We can't tell one part from another. The particles are evenly mixed, evenly distributed, uniform, and the particles are really, really small. That's another thing. Heterogeneous mixtures not uniform. And the particles are larger. You know, like garden salad, chocolate milk, you know, orange juice with pulp, granite. Y'all think of any others?
I think there's blood.
Yeah, blood. Because blood is a mixture of water and proteins and platelets, and you know, in hospitals they can, you know, put a test tube of your blood in a centrifuge and spin it, and all your platelets go to the bottom. Okay, any questions about that? I mean, it's pretty straightforward. Okay, we need to move on to some other stuff. One thing I do want to say about chapter 1 though. Energy is involved in all chemical and physical changes. That's on page 10. We'll learn more about that as we go through this next semester. All right. And we know about the periodic table. That was section 3 of chapter 1. Just a brief intro. Yeah. Periodic table.
Do you need these back or can you put
I just put it all in the basket. Thank you. We know so much about this thing now, don't we? Yep. Okay. This is a very ugly drawing, and it's, you know, going to get messed up, I'm sure. But you got that red stair step line, right? Remember it? Okay. The elements: boron, silicon, germanium, arsenic, antimony, antimony and tellurium. These guys are called metalloids. And remember, they have properties intermediate between metals and nonmetals. And we looked at some samples of them. You know, they can be brittle looking, but they might have a little bit of shine. You know, they got, it's kind of in between, which makes sense. Look where they are on the periodic table. Where are the metals? Yeah, metals are to the left, except for which one, y'all? Hydrogen. You know, it's a non-metal. It's over here because it's, you know, got one electron in its outer level. And then these guys are metals down here. Where are the non-metals? Non-metals are over here, right? So as you go across every period, you got metal, 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 kind of both, and then you got non-metal. What are some properties of metals?
Shining.
You can polish them to shine. You can draw them into a thin wire, which means they're ductile. You can hammer them into a thin sheet, which means they're malleable. And they're good conductors of heat and electricity. Right? Okay, so everything about a metal, the opposite is true of a non-metal. They're brittle. You can't hammer it into a thin sheet. You can't polish it and make it shiny. It's dull. Right? Y'all good with that? Chapter 2. Let's see. Definitions. SI base units. Remember that was page 34, table 1. Be able to convert using factor label. With prefixes in table 2. I will give you table 2. You don't get in college, just remember that. Density is mass divided by volume. So be able to do simple calculations with that. You know, if you got 10 kilogram block and it has a volume of 4 cubic centimeter or 4 cubic meters, you plug in your mass here, kilograms, plug in your volume here, right? Unit is kilogram per cubic meter, whatever your units are. Right, it's not hard. Okay, moving on. Sig figs, accuracy and precision. Take a look at 44. Accuracy, precision. Accuracy is how close. Measurement is to accepted value. Precision is how close. That's not dose. That's close. How close a set of measurements are to each other. percent error is a way that we qualitatively, there's some words. What does qualitative mean? Not even sure what chapter it's in, but it's important. Words. Yeah, words. Descriptive. It's hot in here. Qualitative observation, right? I can't spell descriptive. There we go. Quantitative. Numerical measurements. It is 67 degrees Fahrenheit in this room. Quantitative observation. I will put this video on the YouTube channel. I will send the link to your Remind. It's on YouTube. It's Professor A.E. Jr. A.E. Albert Einstein. Get it? Okay. Yeah. Sadie named it. Okay. And I'll call this Chemistry Fall Semester Review 2015. So you can Google, search it in case you don't have Remind. But if you need Remind, let me know, and I'll get you the keyword. SIGFIDs. How many SIGFIDs there?
1, 2, 4, 1.
Three.
None.
1,
Oh.
2.
Oh, okay.
How many SIGFIDs there? 1. The rules are on page 47. Okay, what about this one? 4. Which ones are not significant?
What's the left?
Ones to the left of what?
The first number greater than 0.
Those are never significant because they're just placeholders. They're just there to show size. Why is this one significant? Zero sandwich. And this is significant because it's at the end of the number and a decimal is present. Okay. Page 49. Let's do it this way. What would that answer be? What, like 3.5?
3.5. Yeah.
7 divided by 0.5, I don't, actually, that'd be 14. What would that be? That's sad, isn't it?
3.5?
14, yeah.
Oh.
14. 14 what?
No.
Meter squared. Meter times a meter, meter squared. Okay, how many SIGFIDs do we round this to? 1, good. Remember, if it's multiply or divide, you look at how many SIGFIDs are in your measured quantities. We got 2 SIGFIDs here,
And 1.
1 SIGFID there, so we need to round that. How are we going to round that to 1 SIGFID?
Oh,
Well, what digit are we going to drop?
probably the 4.
We're going to drop the 4. Is it 5 or greater? No, so we do not round up. So what would we round this to? 0. So what would the answer be? 10. Okay? Very logical. Okay? This is all very logical. You go through the same steps every time. Now, if you add or subtract, you don't look at total sig figs, you look at the decimal place of the least precise measurement. So let's say we had okay, we do the addition, we got what, 0.1, 7, 2, 3, right? Gram plus a gram is what, y'all?
Grams, grams. I mean, no, 2 grams.
It's a gram.
Okay.
I was thinking about it. Sorry.
All right, now, we got to round to sig figs. This is addition. Addition or subtraction, we do not look at, oh, well, that's 4 sig figs and that's 1. No, we look at the decimal place. Which one of these is least precise? The 2. What decimal place does it end in? The 1's place. So what do we round our answer to? The 1's place. So we round it to what? The 1's place. Where's the 1's place, y'all?
What does that mean?
Yeah. So what we round it
3,
to?
3.
Huh?
I don't, quarter around to
We
I know.
round to the 1's place. We want right there. So what means we're dropping that?
So 3, 2, 7.
Yeah. Yeah.
Thank you.
Okay.
I was thinking,
Don't take it on.
okay, I won't speak.
He's all right, y'all. All right. Proportionality. Proportions are on page 55 and 56. Not a big deal. I'm not, not going to ask you, if I do, it'll be one question. Because, we got 6 chapters. I can't ask a lot of one thing, right? Okay. Just look at these 2 graphs. Which one of these would you say the 2 variables are directly proportional? The one on the left or the one on the right? Left. This is a direct proportion, which means as x gets bigger, what does y do? Gets bigger. What is this? As x gets bigger, what's y doing?
Get small.
Gets smaller. This is inversely related. Okay. The model of the atom. The model of the atom. Golly, y'all. We could talk all day about that, right?
Right.
Um, There's our models. So, whose model is that? Dalton. Okay, he proved which philosopher was correct. Democritus or Aristotle? Democritus. Aristotle was accepted for 2,000 years, but he was wrong. Democritus was right, and Dalton proved it, right? With the discovery of the atom. He said the atom was just a solid sphere. End of the line. Okay, whose model is this?
There are 3.
No.
Dang
Thompson.
Oh, wait, was Rutherford?
Okay, Thompson, this is Rutherford. Bohr, and then, quantum. Okay, so he discovered the atom. He discovered energy levels, right? And this is the current model. Okay?
The last one's a 3D one, right?
Yeah, that one's 3D. This one's 2D. Okay. What is the electron configuration for silicon? Silicon. 1s2. Or you said this is what you need help with, right? We go to hydrogen. 1s2. Come down to the second row. 2s2. Okay, go across to the P block. 2p. How many do we count across? 6. 3s2. Why is it 2?
Stop.
Right, you stop when you get to your element.
That's right.
Okay? What would be the noble gas notation?
Hang on.
Ne in square brackets. Now you just come down and finish it. What's after Ne? 3s2, 3p2. Okay, and then, orbital notation is the arrows. I'm probably not going to ask about that because we won't really use it in the future. Okay, and then all this bonding stuff. Huh? Okay, some more about the periodic table. Let's look at the periodic table again. Group 1. Group 1, the family is called alkali metals. Most reactive metal. Group 2, alkaline earth metals. Less reactive than group 1, but pretty reactive, as we saw the other day with the magnesium. Okay. Groups 3 through 12 are the transition metals. And what about group 17? Halogens. What's group 18? Okay. What's so special about noble gases? Unreacted. Halogens, most reactive nonmetals. Transition metals form very colorful compounds. So I think that's enough to put together a pretty good review of the semester. Okay? All right. So if you want, watch that video. Yes. Progress reports.